also try to share my screen with you. So last week we have yesterday we actually explained the definitions of the equivalent single axial load, ESAL. We also showed the calculation about the one factor, which is called the equivalent axial load factor. And this factor is very important for us to estimate the ESAL. And with this one, we can identify the traffic volumes applied for the pavement based on the fixed vehicle criterion. And the value of the EALF could be estimated based on the equation stochastic model from defined by Ashton. With that, you have the features of the pavement. You have the loadings for the from the axials, and then we can estimate the load factor, equivalent axial load factor. This is one stochastic model, but in the study about the pavement design, there are also some theoretical models to show the estimation of the equivalent load the load factor. By the way, this one equivalent axial load factor sometimes it's also called the LEF, the load equivalency factor. So if you find something in the homework assignment or the or in other book, they should be the same thing. And theoretically, we can identify the equivalent load factor or the load equivalency factor based on the failure criterions. One of the major failure for the pavement structure is fatigue cracking, which comes from the repeated loading to one more specific regions of the pavement. And this equation defines the fatigue cracking with respect to the strain and the and also the resilient modulus of the surface layer. And with this analysis, with the fatigue cracking criterion, the load factor could be estimated theoretically as WT, which is also defined as WT18 divided by WTX. That would be the epsilon x divided by epsilon 18 to the power of 4. Here, epsilon x is the tensile strain at the bottom of the asphalt layer due to the x-axis load, and x18 is the tensile strain at the bottom of the asphalt layer due to the standard axial load. And with this one, it shows that what's the equivalent value of the load, the x load, to the standard load with respect to the tensile strain. So the tensile strain will, depending on the value of the tensile strain, usually if it's a larger value of the tensile strain, it indicates that there's a higher possibility of the fatigue cracking. And also, if we consider the load, the x-axis is in a single axial, then the equivalent single axial load factor could be Lx divided by 18 to the power 4. Here, Lx is just the load of the single axial. But if it's in a tandem or trident axial, you cannot use the standard the constant value of 18. Instead, you need to find out the standard load for the tandem or trident axials. So this is the theoretical estimation of the loading factor. Now let's go to see one example to understand how we can use this theoretical model to estimate the equivalent load equivalency factor. So assuming that we have a pavement with the terminal serviceability PT equal to 2.5, the structure number of 5, and we want to determine the load factor for 5,000 pound and 50,000 pound single axial load. And also we want to identify the ESA, the load factor of 15,000 and 18,000 pound tendon axial, given the ESAL of 32 kilopounds tendon axial as 0.857. So for this problem, let's start with the single axial for single axial. So for the single axial, we know that the LS will just be 18. And in this problem, we want to solve two situations. So we have the LX equal to 5,000, so it's 5 kilopounds. And the second situation, LX equal to 50 kilopounds. And for the first situation, the equivalent loading factor will be LX divided by 18 to the power of 4. So that is 5 divided by 18. And it gives you the value as 0.006. So this is the theoretical value for the equivalent loading factor. And for the second one, we have LX equal to 50. And this one will give you a much larger loading factor, which is 59.54 for the second situation. And the next thing we want to consider is the what happens if it's in the tendon axial. In the tendon axial, we will not know what's the value of LS because it's not mentioned in this problem. But we know that the ESAL, EALF, the load factor, will equal to 0.857 if the load is 32 kilopounds, which means that if it's 32 divided by LS, this one should equal to 0.857. So this is the condition we have. And now we can go to check the what's the load factor at LX equal to 15 kilopounds and LX equal to 80 kilopounds, the second situation. So for the first one, we have EALF equal to 15 divided by LS to the power of 4. And we don't know the value of LS, so we can just simply do the conversion. 15 divided by 32 times 32 divided by LS to the power of 4. So with this one, you can get the 15 divided by 32 to the power of 4 times 32 divided by LS to the power of 4. So this will give you the result for the second part. For the second part in this equation, this one is a 0.857. This is from the assumption. Then you can easily get the equivalent load equivalency factor as 0.041. Well, you can then apply the similar process to find out the value with the 80 kilopounds load. So with this one, you get the result as 80 divided by 32 to the power of 4 times 0.857. That is 33.48. So this is the way for us to calculate the theoretical load equivalency factor, and it actually applies for both single and tandem axials. In the literature, there's another type of the failure criterion, which is related to the other permanent deformations. With in this kind of criterion, they will define the other type of the permanent deformation as also a function of the strain, the tensile strain at the bottom of the asphalt layer, and they will try to calibrate this model to find out the coefficients of F2 and F5. Generally, for the Asphalt Institute, they find out F5 equal to 4.477. For the Shell company, they find that the value is 4. By the University of the Nottingham, it's 3.5. It's all around 4. So in general, we will just assume that F5 equal to 4.0. And with that, we will have the similar result, EALF equal to LS, the LX divided by LS to the power of 4. And here LS is the LX is the load for different type of the axials, and LS is the standard axial load. So this is the other type of the permanent deformation. And so for all the previous discussion, we actually measured the load equivalency factor or the equivalent axial load factor. So this will be LEF and or EALF will be the same. So those are all about the flexible pavements. But for the rigid pavement, the equation will be a little bit different. From AASHTO, we also have a stochastic model to estimate the load equivalency factor, and this equation will be similar to the flexible pavement. The only difference will be the coefficients. So those coefficients will be a little bit different from the flexible pavement, but the definitions of all the other parameters will be the same. And we can then also find out the load equivalency factor from this stochastic model. So if you know how to calculate the load equivalency factor with the flexible pavement, you must know how to get it for the rigid pavement. This table actually shows the common or the typical values of the load equivalency factor for different type of the axials, including the single axials, the tandem axials, and trident axials. But remember that this one is only applied for a specific rigid pavement with the thickness of the flex of the PCC slab of 9 inches, and the terminal serviceability of 2.5. This is the table to show this case, and you can find out the load factor for different axial loads. For example, if we consider an axial load of 10 kilopounds for the single axial, the load factor is 0.082. For the tandem, it's 0.018, and for trident, it's 0.005. And basically, if we increase the axial load, the load factor will increase for different axials. And of course, at the single axial load, will usually have the larger loading factors compared with the tendon and trailing axles because they only have the one pair of the tile to support the load. So this is the load factor for the rigid pavement. And once we have already received the load factor, the next thing we can do is identify the equivalent single axle load with respect to the traffic count we obtained from the field and try to estimate the ESAL over the design life of the pavement. So here we have several equations to calculate the ESAL. Basically, we will first categorize the vehicles in the on the road into several groups, assuming that we have m groups of the vehicles. So that could be the passenger cars, the light truck, the heavy truck, medium truck, the heavy truck, the bus, and so on. And for each load group, we will have an equation to estimate the initial number of the repetitions per day for the for that type of the vehicles. So here the total number of the repetitions per day for that group of the vehicles, and that will be Ni. Ni will equal to the N0I times G times D times L times 365 times Y. So here in this equation, N0I is the initial number of the repetitions per day for the ice group, and G is the group factor. And we will have more introductions about what the group factor it is. And D is the directional distribution factor, and L is the length distribution factor, and Y is the design period in years, how many years the pavement will last. And if the design is based on the standard axle load, a single axle load, which will be represent to 18 kilopounds or 80 kilonewton, then we can estimate the value of N0I, that will be the initial number of the repetitions, as Pi times Fi times ADT0 times T times A. Here, Pi is the percentage of the total repetitions for the ice group. Fi is the equivalent axle load factor of the ice group, or the load equivalency factor. And ADT is the average daily traffic. How many vehicles vehicles in this group were traveling on this on the pavement every day? So it's the average daily traffic, and T is the percentage of the trucks in the average daily traffic. So how many of them will be the truck? And A is the average number of the axles per truck. So how many axles in this type of the truck? So if we combine these two together, you can find out the number of the repetitions during the design period for the ice group with respect to the standard axle load. And if you summarize all the groups together, so which means that if you do this, summarize all the M groups for the Ni, you can find out the equivalent single axle load over the design life. This will shows the full equation for you to get the ESAL. And in this equation, you can see that there will be only two factors related to the group, and that will be Pi, the percentage of this group, and Fi, that will be the equivalent axle load factor for the ice group. And if you summarize them together, times the value of A, here A is the the average number of the axles per the truck. Then you can get the calculate the truck factor. So the truck factor will shows the weighted value of the truck, all the trucks in the estimation of the equivalent axle load. So if we know the if we have the truck factor and if we have the average daily traffic, the group factor, the lane distribution factor, also the directional distribution factor, and the number of the design years, then you can calculate the equivalent single axle load for 18 kilopounds or 80 kilonewton single axle load with respect to the truck for the pavement. And this would be the simplified equation for you to calculate the ESAL. With that, we can have some. We have the table to show the typical values of the distributions of the truck on different class of the highways. For example, for the rural highways, if it's in the minor arterial, then usually for the single unit truck with 2 axles and 2 tires, it will occupy 71%. For 3 axle or more, it usually only takes around 4%. And in total, we have typically we will have 86% of them would be the single unit truck. And for the multi-unit truck, usually we will only have 14%. We only have 14%, and for 4 axle or less, that will be 3%. That will be 3%, and for 5 axles, that will be 11%, and so on. So this is for the rural area, but for the urban area, you will also find out some. You will find out there will be some difference. Usually in the urban area, there will be more passenger cars and small trucks. So what you will observe, like for the minor arterial, there will be like 95% of them could be the single unit truck, like a pickup truck and something a little bit larger. But for the multi-unit trucks, the percentage will be much smaller. It's only 5%. So that will be the difference about the the rural and the urban system. Usually this will just be the typical value. For the specific pavement that you're trying to design, you need to collect all these percentages by yourself in order for you to calculate the truck factor. And for the distributions of the truck factor under different class, we can also find out the values for the rural system and the urban system. Generally, if we still take the minor arterial as one example, for the single unit truck, the overall truck factor is around 0.08. So those would be considered as the small or the light truck. So it has less impact to the pavement structure. But for the multi-unit truck, the truck factor could be as high as 0.97. It's much higher. It's 10 times higher than the single unit truck. So they have more severe impact to the the major cause of the failures of the pavement structure. For the urban system, the value is actually much smaller. So usually you will for the minor arterial, for single unit trucks, the truck factor is only around 0.04. For the multi-unit truck, they will be around 0.67. So this is just some typical value in the United States. And if for your own design, you have to specify or you need to calculate the truck factor by yourself. And the other things about the growth factor will calculate how many trucks will moving in the future years. So usually you will be provided with the growth rate, the annual growth rate, which would be the value of R here. So R is the annual growth rate. So it tells you what's the percentage of the increase about the traffic in that area. Usually we can use a very simple model to calculate the growth rate. For the simple model, the growth rate G will be half of 1 plus R to the power of Y. Here Y is the design years. How many years for the whole life of the pavement? If there's also a simplified model from the Portland and Cement Association PCA model. So it assumes that the growth factor equals to 1 plus R to the power of 0.5 Y. And for the asphalt institute and ASHTO, they propose their own model. They assume that the total growth factor over the designed years from year 1 to year Y will be 1 plus R to the power of Y minus 1 divided by R. So this would be the value of G times Y. It's different from the previous two. So for the AI and the ASHTO method, G will equal to 1 plus R to the power of Y minus 1 divided by R times Y. So this is the calculation of the growth factor. It will show you how the number of the traffic is changing over the years. And now let's see one example to see how we can calculate the growth factor. Assuming that the annual growth rate is 3.5% for the traffic, and the designed period is 30 years, we want to find out the growth factor of all the three models. So we can start with the simple model. So for the simple model, G equal to 1/2 of 1 plus R to the power of Y. And here in this example, R equal to 3.5%, and the Y is the designed year, that is 30. So we have the value as 1/2 of 1 plus 0.035 to the power of 30. And this will give you the growth factor of 1.9. So this indicates that if you have 100 vehicles in the current year, after for the whole design period, every year the growth rate will be 1.9, which means that next year will be increased to and at the end of the design life will be 190. So for the that's for the simple model. The next model is the PCA model. So for the PCA model, we have G equal to 1 plus R to the power of 0.5 Y. So we have the value of R as 0.035 and design year 30, which will give you the value as 1.68. And we also have the last model, third one, the AI and ASHTO methods. So with this model, we have G equal to 1 plus R to the power of Y minus 1 divided by R times Y. So that is 1 plus 0.035 to the power 30 minus 1.035 times 30. it will give you the result as 1.72. So you can see that all these three values are pretty similar to each other. They are under the similar scale, even though the absolute value is not exactly the same. Usually we will utilize the last one, the AI or the H2 model, to calculate the growth rate, especially for the design of the flexible and flexible and rigid pavement with the AI and the H2 method. The next thing we have to consider for the estimation of the traffic volume and load is the directional distribution factor. So this one will tell you what's the percentage of the truck traveling on each direction. Usually we are considering a two-directional road. Well, this is one example. If this road has two lanes, but each direction will only have one lane, and you find that the lane on the left is has 47% of the trucks, and on the right has 53%. Then we have to consider this one as the designed lane. So we will try to use the 58, the one with a larger value, to design the pavement. And this means that we will try to make sure that the pavement can support the worst case with the highest volume of the truck. And this is about the directional distribution factor. We also have some typical values about the directional distribution factor. Usually for the two-lane highway, the lane in each direction is the designed lane. So if these two lanes are separate, and we can consider that they will be in a separate pavement project, and in that sense, the lane distribution factor is 100. But if we have the multiple lane, then they will be very different. For the if there are two lanes, if there's two lanes in each direction, usually the outer lane, which would be the right lane, in United States and some other countries, in Canada, will be the right lane. In UK, that will be the left lane. So we consider that those would be the outer lane. If depending on the average daily traffic, if the daily traffic is around 2,000, then almost like 94% of them will be traveling on the outer lane, 94% of the trucks. And if it's 10,000, around 81% of the trucks will be traveling on the outer lane. But if there are three lanes in each direction, the situation is different. For the inner lane, it has a very small percentage, which would be the left lane. If we consider the traffic of 10,000 vehicles per day, we only have 7%. For the center lane, it's 25%. For the outer lane, which would be the right lane, it's 68%. So this is actually the lane difference. And of course, we want to design the pavement based on the lane with the highest percentage. So for example, for the two lane with 1,000 traffic, we need to consider the lane distribution factor as 81% instead of 19%. We always choose the one with the highest percentage of the trucks. So this is the reason we say that usually the design of the pavement is based on the outside lane, and we set that outside lane as the designed lane. So this is the lane distribution factor, and well, for here we're gonna have one specific one example, like for this traffic, for this specific 2-lane road, we have 25% of the track on the left lane, 75% on the right lane. Then this one would be the designed lane. And if it's in the three-lane road, we have 80% on the left lane and 39% in the middle lane and 53% on the right lane. Then we're going to use the right lane as the designed lane. So this means that we always design the pavement for the worst situation with the highest volumes of the trucks. And you have to choose the design lane based on the percentage. It's not for some real case, it's not necessary to be the right lane, just based on the which lane has the highest percentage. And this is based on the PCA model. This figure actually shows the lane distribution factor with respect to different average daily traffic. Usually there's a linear relationship between the lane distribution factor, the horizontal lane distribution factor, which would be the horizontal axis, and the vertical axis is the average daily traffic in thousands. So basically, with usually with a smaller number of the average daily traffic, more trucks were moving on the outer lane, and with a larger number of the daily traffic, the road might be congested, so the truck might move to the middle lane or even to the left lane. So that's the lane distribution factor. And here we also have some typical lane distribution factor for the from the AASHTO design. If we consider the one-way traffic, depending on the number of the lanes, for 1 lane, 2 lanes, 3 lane, 4 lane. If there's only 1 lane, definitely all the trucks is moving on that lane, so that percentage is 100. If there are 2 lanes, it usually is around 80 to 100. If it's 3 lanes, there should be around 60 to 80. If there are 4 lanes, then in the designed lane, there will be around 50 to 75%. But if we consider the two-directional freeway, like there isn't any barriers between the eastbound and the westbound, then we have to consider the entire freeway as one pavement structure, one pavement project. So for 2 lanes, which would be the situation, 1 lane to the left, the other lanes to the right. Then the design traffic will be the percentage of traffic will be 50% for each side. This would be a typical value. For 4 lanes, that would be another situation. So on each direction there will be 2 lanes, so you totally have 4 lanes, and the designed lane will typically have 48% of the truck. It could be varies between 35 to 48. Typical value is 45, sorry. And if there are 6 or more lanes, then the typical percentage is 40, and it varies between 25 to 48. So that's the lane distribution factor. And now we have all the information. So the next thing we have to do is try to calculate, see how we can estimate the ESAL. So here I will go through one example. Assuming that we have the 2-lane major rural highway, and it has the average daily traffic of 4,000 during the first year. And in this traffic, in this count, 25% of them will be the truck, and the growth factor, annual growth factor, is 4%, and the designed lane has 50% of the 50% of the trucks. And also we assume that if the distribution of the truck is the same as we show in the previous table about the truck factors, then it wants us to see how we can calculate the ESAL for the design period of 20 years. So first of all, in this problem, we want to summarize all the assumptions provided to us. So we have the ADDT 0, which is the initial average daily traffic, as 4,000. We have the truck factor, not the truck factor, the percentage of the truck as 25, and the annual growth rate as 4%. And also we have the lane distribution factor for the as 50% for the designed lane. And as you know that this is a 2-lane rural road, so the directional distribution factor would be 100. So because the all the vehicles in the same direction should drive in that dedicated lane. And the next thing we need to find is the truck factor. What's the truck factor? And this one wants us to go back to the previous truck factor distribution table to get the truck factor value. And we can use the let me just return to the table. So this is the truck factor table. We are considering a 2-lane rural highway, and I guess this is the one. The percentage of the we know the this is in a highway, so that will be the interstate highway, and we will then know the distributions of the trucks. The distributions of the trucks would be 58% of them could be the single unit truck, and 47% of them could be the multi-unit truck. And also we can find out the truck load factor for all the single unit truck is 0.06, and for all the sorry, I guess I try to identify the wrong, sorry, I try to identify the wrong type of the highways. So for the rural system with the average daily traffic of 4,000, this will just be in the principal road. It's not an interstate. Usually interstate will have the wider road. The for the interstate, the for each direction usually will be 2 lanes, not for the 2-lane road. So the so it will have 73% of the single unit truck, 21% of the multi-unit truck, and for the single unit truck, the truck factor is 0.08, and for the multi-unit truck, the factor is 1.21. In total, the truck factor is 0.38. So you can actually calculate this truck factor based on the equation here. So this is the formula for you to calculate truck factor based on with their percentage. And for this example, I will just make it simple. We have the truck factor of 0.08 from the table, 0.38 from the table, and then we need to calculate the growth factor. So here we're going to use the AI and the ASTO method. we can find out the growth factor with respect to the whole design life, G times Y, as 1 plus R to the power Y minus 1 divided by R. So we know R is 4%, and design life is 20. So this will give you the growth factor for the whole design period as 29.78. And then the estimation of the ESAL would be straightforward. We can call their definition ADT 0, the initial average daily traffic, times the percentage of the truck, times the truck factor, times the growth factor, times the directional factor, times the land distribution factor, times the number of the days over the year, times Y. And here you can see that we calculate the G times Y, so we can put a G and Y together. And with that, you get the answer of the ESWL. Average daily traffic is 4,000. The percentage of the truck is 25%. The truck factor 0.38. The growth factor 29.78. The distribution factor is 100. The land distribution factor is 0.5. And we have 365 days for the for each year, and this will give you the total number of the traffic as 2,065,200. So it's approximately 2 million over the design life, and this is just for an major rural highway. And this is the example for us to calculate the ESAL. So I think I have completed all the contents about the estimation of the traffic loadings and the volumes. With that, we have 1 minute left. Do you have any questions or about the estimation? Okay. If no, that'll be all today. And for the for your midterm, the TA and I will start to grading your midterm exam. And in the meanwhile, if you have any concern, just feel free to contact us. And we will try to get the result back to you by early next week. So if you find out there's anything wrong or anything that any mistake about the grading, let us know and we can correct them as soon as possible. Okay. I guess that's all. If you don't have any questions, I will close the meeting today. And I really appreciate your time for the class. And with that, I will see you next week.